Hello, it's Stat 134, Lecture 21. Last time we started talking about continuous distributions, in particular probability density function, which is a non-negative function that integrates to 1. Notable thing about it is that the probability of a particular point is always 0. So that when we say the probability that x is greater than or equal to a, that's exactly the same as the probability that x is greater than a. So we'll often be sloppy about endpoints. Furthermore, another thing to note is that when I make a graph of the density function, the height of the density function has units probability per unit length. So right? So the area, in this case, the area of the green bar here is the probability, and the length of the bar is the unit length. So area over the unit length is the height. So those are the units for the height of the density function. Furthermore, we talked about a change of scale, and a change of scale is just basically for a and b constants, ax plus b. Today what we're going to do is we're going to talk about a cumulative distribution function as well as the exponential distribution. So the cumulative distribution function is another way to characterize a distribution besides the density. So the density, f of x, the CDF is the probability that x is less than or equal to x, which is the integral from minus infinity to x of the density dx. So for example, if x is uniform, then f of x has non-zero values for x between 0 and 1, and so the CDF is just the integral from 0 to x, which is just x. So next we're going to begin talking about exponential distribution, but first let's discuss the memoryless property of the geometric distribution. So if x is geometric p, remember that x is the number of trials till your first success. So the x being geometric is defined by the geometric formula, which is probability of x is k is q to the k minus 1p, but it's also characterized by the probability that x is greater than k is equal to q to the k. The reason for this is that if you know that the probability of x is greater than k, you can write the probability of x is equal to k as the probability of x greater than k minus 1 minus the probability of x greater than k. And so either the geometric formula or the probability that x is greater than k characterize the geometric distribution. And of course, the probability that x is greater than k is 1 minus the CDF, and I already said that the CDF characterizes the distribution. So now we have a theorem that the geometric distribution is the only discrete distribution with values that are natural numbers having the memoryless property. The probability of x greater than k plus j, given that x is greater than j, is equal to the probability that x is greater than k. In other words, if you take more than 10 tosses to get your first heads, what's the chance it'll take you more than 13 tosses to get the first heads? Well, it's just the same as the probability that it takes more than 3 tosses to get your first head. In other words, given that you haven't gotten a head in the first 10 tosses, you can basically forget that ever happened and just start from scratch. So that conditional probability is equal to the unconditional chance of needing more than 3 coin tosses to get your first heads. So it's a pretty interesting and important property. So let's see the proof. Let's first show that if x is geometric, then it has the memoryless property. So here I'm just going to use Bayes' rule. Sorry, I wrote G here, but I meant X. So I'm going to use Bayes' rule, and because K and J are natural numbers, if X is greater than K plus J, then X must be greater than J. So that X greater than J is redundant. And then we have that this ratio is Q to the K, which is the probability that X is greater than K. So that shows the memoryless property. Now conversely, for positive integers K and J, if I have the memoryless property, I can write the left-hand side using Bayes as probability that X is greater than K plus J over probability that X is greater than J, cross multiply to get the probability that X is greater than K plus J is equal to a product of probabilities, probability of X greater than J times the probability that X is greater than K. So now let's let Q be probability that X is greater than 1. So we're going to show that the probability that X is greater than J is Q to the J by induction. Now, if we do show that, then we'll conclude that X is geometric, because remember, X is geometric if and only if not only the geometric formula holds, but also the probability that X is greater than J is equal to Q to the J. So the base case holds trivially here. So we're going to assume that the probability of X is greater than J minus 1 equals Q to the J minus 1. And then the probability that X is greater than J, we see by using our assumption here, is equal to Q to the J, so X is geometric. So now there are only two distributions that are memoryless. For discrete x, 1, 2, 3, and so on, it's geometric. For continuous t greater than 0, it's exponential. The proof of the memoryless property for exponential is similar to that for geometric. So exponential is very much analogous to the geometric, but for the continuous case. Let's see what it is. So the exponential distribution is, by definition, it's a random time t has exponential distribution with rate lambda greater than 0. In other words, we write t belongs to the exponential lambda. If t has density, f of t is lambda e to the minus lambda t for t greater than or equal to 0. So I've drawn a graph here of an exponential. So exponential decay, it always looks like this. Here t is non-negative. So t is the time until your first success, where lambda is the rate of success. So success here, success is usually some kind of death when it comes to the exponential distribution. For example, t is the time until a light bulb burns out. So we can look at the CDF and survival function for exponential. When t is exponential, you can compute the CDF and see that it's 1 minus e to the minus lambda t. We write p is t greater than little t. It's called the survival function because it means that success hasn't happened or death hasn't happened before time t, so you've survived. And probability that t is greater than t is 1 minus e to the minus lambda t, which is just e to the minus lambda t. So this characterizes the exponential, just like the survival function characterizes geometric. So we say that t is exponential if and only if probability of t is greater than t is e to the minus lambda t. So can we think of geometric as a discrete version of the exponential? Yeah, kind of. Here's how. So let x be geometric p. So x takes values 1, 2, 3. And let p of x be a change of scale of x. So px takes values p, 2p, 3p, and so on. So we're going to show that in the limit, px becomes the exponential with lambda equal to 1. And the limit is p goes to 0. So the probability that px is p, that's just the same as the probability that x is 1, which is p, and the probability that px is 2p is qp, and so on. So you can draw the probability mass function for px, and it'll look like what I've shown here. And as we discussed, the height of the bars here are probability per unit length. So the height of the first bar is always 1, no matter what p is. And so it's 1 probability per unit length is the units there. And so I'm just going to erase this. So now you can compare this graph here with the density of exponential lambda. And so essentially, as p becomes finer and finer, smaller and smaller, we're essentially going to end up with this exponential density function. Let's see how that works. So we have the Taylor series. E to the x is 1 plus x squared, and so on. So e to the minus x can be approximated by 1 minus x for small x. For small x. Okay, so here, now the height of a bar at time t equals kp is q to the k, right? You can see that here. And q to the k is 1 minus p to the k, and 1 minus p when p is small is approximately e to the minus p by our Taylor series approximation here. So this is just e to the minus kp, which is e to the minus t. So as p goes to 0. So that's how the heights, as p becomes smaller, becomes an exponential decay, e to the minus t. So here, lambda is 1. So the height of the first bar is always 1, no matter what p is. The units of the height is probability per unit length. Unit length here is p. As p goes to 0, the height of the first bar stays at 1, and we get lambda is 1. So, right, the y-intercept is 1 in this case. Lambda is called the instantaneous death rate, right? So lambda is probability per unit length, but the unit length is going to 0 here. You can interpret lambda as the probability of success during an infinitesimally small time interval. So in summary, x is geometric p, then p to the x goes to exponential 1 as p goes to 0. So that's the best way to think about the exponential as a limit of geometrics as p goes to 0. So we ended with an example here where x follows an exponential distribution with parameter lambda is 5, y is the ceiling of x, and we want to know what's the distribution of y. So the values of y are the natural numbers, and the probability that y is the probability that x is between minus y minus 1 and y. I'm not worrying about endpoints because x is a continuous distribution. So here I'm just using the definition for exponential and doing some algebra here, and you'll see you'll end up with if I call p 1 minus e to the minus 5, then q is e to the minus 5, and I have q to the y minus 1 p. So